All right, so cyclohexane chair structures. They are a way of showing the conformation of the molecules, and they take some practice to draw them well. But it's really important that you can draw them well, because if you talk to other organic chemists out on the town or at your organic chemistry cocktail parties, and you draw a chair structure that doesn't look like a chair structure, no one's going to know what you're talking about. So it's really important to practice these things. Um, Here's a chair structure right here that I've already drawn up. And on your note packet on the first page, it says that it gives a couple bullet points. So one, chair structures are three sets of parallel lines. So I'm going to kind of draw another chair structure right next to this one that kind of illustrates those three sets of parallel lines. So the first parallel lines are the two on the sides. So if we draw one of them, and then we're going to draw another one that's roughly parallel. So that's two of the parallel lines. Now we'll switch colors. So this line here should be parallel to that line. So we'll draw that and this. And they should be roughly the same length as well. So we got two sets of parallel lines, and then the third parallel line is going to be here and here. So that's a pretty good chair structure. Sometimes I draw chair structures and I'm like, I really hope no one sees that. That is an ugly chair structure. I look like an idiot. But these ones look pretty good. So this is what you're going to be practicing on your own. Just doodle it on a piece of paper while you watch your Netflix. Whatever you need to do, get these chair structures down. Draw them well. The second bullet point here says that each carbon has one equatorial and one axial substituent. So what we saw in the last video is that the reason why these cyclohexanes adopt the chair structures is so that all of the substituents are staggered. So each individual carbon is actually a tetrahedron in and of itself. So what does it mean for a substituent to be axial or equatorial or axial? So where have we heard those terms before? Well, let's think about a globe. So the world is a big spherish type thing. And it has an equator, right? So the equator is around here. So this is the equator. It goes equator. Yeah, so I was going to write equatorial, but I just needed equator. But the equator, the equatorial stuff, is on the sides. What about the axis of the globe? Well, the axis goes through the globe. So what does the globe do? It spins on its axis. So this is the axis. So what does that look like? Well, the axial substituents are going to go north and south, right? They're going to be up and down. The equatorial substituents are going to be east and west. They're around the sides. So let's look at our model again. So on this model, what we can see is that, like, if the cyclohexane is here at the globe, and the substituents that are up, so this and this are up, this and this are down. These are kind of the northern substituents. These are the southern substituents. Those are all those are axial. They're along the axis, up or north and south. What about the equatorial substituents? Well, they are going east and west. So this one's far out east, this one's far out west, and as we spin it, we see that we have an equatorial proton on each of the carbons, and each of the carbons also has an axial proton. So how does that look on the structure as we draw it here? Well, each carbon is going to have two protons on it, and they should also go, the equatorial protons should be parallel with some of the lines. So this line here is roughly parallel with this pink line. And this is the equatorial hydrogen. This here is also an equatorial hydrogen. It's roughly parallel to this blue line. So this is the other equatorial proton. The other protons are just going north and south. They are the axial protons. They aren't necessarily parallel with anything else. They're just north and south. But each carbon has an axial proton and an equatorial proton. So that's what we see here. That's how we draw the cyclohexane structure. So pause the video for a minute and try and draw a few more of these. Do a little practice, and then we'll restart on the next idea, which starts on page 2 of the online packet. All right, so on the start of your next page, it says wedge/dash on the skeletal structure. So here's our skeletal structure. We have wedges and dashes. So wedge dash on the skeletal structure does not correlate to axial/equatorial on the chair structure. So here we have the skeletal structure. We have a wedge and dash, and we've labeled the protons on these wedges and dashes blue and red. Kind of, it might look at random here because the blue one's on the wedge here, the blue one's on the dash there. But how does that correlate to the chair structure is kind of the next question. So first, let's label the carbons of that chair. So we have 1, 2, 3, 4, 5, 6. I've only put the hydrogens on 1 and 2. You have the hydrogens on all of them in your note packet. But let me draw those in. So the red is going to be here and here, and the blue is here and here, what I've drawn over here. So what else is on your note page? On your note page it says that each carbon has one substituent that is, quote, up, and one substituent that is, quote, down. So what does that mean? Well, we have a carbon here, and we have 2 substituents on that. Which one would we call up versus down? Well, this hydrogen here is higher than that one, so let's call this the hydrogen up, and we'll call this the hydrogen down, because for that specific carbon, this one's up, that one's down. For carbon 2, this is the hydrogen that is up. It is higher than this one here, so this is the hydrogen down. So why do we have to label them up versus down? Well, it's because we kind of have 2 ways to describe our hydrogens. We can call them up and down, but we can also call them axial and equatorial. So take a minute, label the hydrogens I've indicated as axial, equatorial, and then try and fill in the blanks down here. It says that if a substituent is wedged, so this hydrogen here was wedged over here, then that substituent must be blank on the chair. If a substituent is dashed, then that substituent must be blank on the chair. So take a minute to fill that in. We saw that if a substituent is wedged, so this blue hydrogen is wedged here, it is up on the chair. This pink hydrogen is wedged here, it's also up. So maybe we can conclude that if a substituent is wedged, it must be up on the chair. Conversely, if we have the dashed bonds, so here at position 1, the dash bond is to the red H, and that H is down here. Here the dash bond is to the blue H, that H is down over here. So if a substituent is dashed, it must be down on the chair. So this process is really important for putting the substituents where we need them to be on the chair. And I want to reiterate what we said at the top. The wedge/dash on the skeletal structure does not correlate to axial or equatorial on the chair structure. How does that show? Well, this H is axial, This is equatorial. This H is equatorial. This H is axial. So what we see is that on carbon 1, the wedge is axial and the dash is equatorial. On carbon 2, the wedge is equatorial and the dash is axial. So the wedge dash does not correlate to axial equatorial. What the wedge dash correlates to is if it is up or down. So those are the general basics of how we take a skeletal structure and convert it into a chair structure. And that's the really first, most important part of drawing conformations of cyclic molecules, and two, and more importantly, impressing your friends at the organic chemistry cocktail party. I mean, guys should all draw them individually, take those chair structures, anonymously putting them up with numbers, and then you can rate who has the best chair structure of them all, and then that person gets some type of reward. Whatever the reward is, that is up to you. And let's get good at drawing these chair structures.